It is time to talk about projectiles. And in physics, a projectile moves only under the influence of gravity. Okay, so this is a moving object. It moves under the influence of gravity. So, technically, if you jump off the top of the building, you are a projectile. Don't do that. But projectile motion is a good way of learning about two-dimensional motion because gravity gives us a constant acceleration. We can do this algebraically, and if that's the only influence on the motion of the object, then the movement is relatively simple, and it gives us a good opportunity to understand some of these natural phenomena. So if I if I throw a stone and I throw it horizontally at some velocity so that it travels parallel to the ground initially as it leaves my hand, most of us are able to ascertain that its trajectory will not remain parallel to the ground. And of course, the reason is because of gravity. So as the projectile leaves me, it will follow a trajectory, something like this curved path. And the reason for that is because at every instant of that projectile's motion, this stone that I've thrown, this projectile, the only influence on it is the gravitational force, which causes it to accelerate toward the center of the earth at a constant acceleration, which we know is 9.8 meters per second squared. And that change in velocity is in that direction, toward the ground. So acceleration, change in velocity. The velocity changes in the direction of the acceleration. This acceleration is down, and so the projectile curves downward and follows this arched path. And what's interesting is that we can separate the horizontal or X motion of this projectile from the vertical or Y motion of this projectile. If we were to take some firearm, a handgun, and we were to fire a bullet horizontally. Now, obviously don't do this in populated areas, but we were to take this handgun and fire a bullet that leaves the handgun parallel to the ground. So as the bullet leaves the handgun, the instant it leaves the handgun, gravity will start acting on it. If it didn't, then the bullet would fly in a straight line, and eventually leave the earth as the earth curved away from it. But that's not what happens. The bullet falls and eventually lands on the ground some distance away. If we took a second bullet at the same height as the bullet in the gun, the same vertical distance from the ground, and the instant the gun is fired and the bullet leaves at some high velocity to the right, we drop this bullet from rest. Drop from rest. So we drop the bullet on the left from rest the instant we fire the gun on the right. Well, those bullets will hit the ground simultaneously. The bullet on the left will arrive at the ground the same time the bullet on the right arrives at the ground. The only difference is that while the bullet on the right fell toward the ground with the same acceleration and reached the ground at the same time, it had a very large velocity in the x direction, the horizontal direction. So it moved, it was displaced in the x direction, and that velocity, that is horizontal, multiplied by the time that it took the bullet to fall vertically. So the motion in the horizontal or x direction is independent of the motion vertically in the y direction. And this allows us to analyze the motion of a projectile without having to use calculus. So we can break apart the motion into vertical and horizontal motion, and if we look at each independently, then the motion of the projectile remains something that we can deal with algebraically. So let's take a look at some kind of simple projectile. Let's say a person. So this individual is running to the right, and they are running at a constant velocity of 4 meters per second. So this is an individual who's quite a bit faster than I am. And this velocity is constant. So that 4 meters per second. And the issue, though, is that this individual is running toward the edge of a cliff. And let's make it be interesting, but not too bad. We'll let them land in water. So there's some water down here. And this is 8 meters from the top of the cliff to the water below. So the instant that this individual runs off the edge of this cliff, their velocity is 4 meters per second parallel to the water's surface, or in the x direction. And what will they do vertically? Well, in the vertical dimension, upwards and downwards, this individual's motion will be identical to the bullet that was dropped. They will start from rest and accelerate toward the center of the earth under the influence of gravity. So let's see if we can figure out how far this individual lands in the water from the cliff. Let's call that X. Seems like a reasonable thing to call that. So how far they land from the cliff, they land in the water. And let's do something else. Let's figure out the velocity that this person as a projectile will have when they land in the water. So we want to figure out x. Find x, that's the distance from the cliff where they hit the water, and let's find their velocity at impact. That's impact with the water. How fast are they moving? What's the velocity when they reach the water? Now, for projectiles, the actual contact with the water is not part of this problem. For any projectile, once it lands on the ground, that's not part of the problem. Our problem ends the tiniest fraction of a second before the projectile collides with anything else. So if you could imagine, the width of a proton from the ground, so essentially on the ground, but once two objects come into contact, that's a collision. That's an entirely different flavor of physics that we will get to. But for now, and for projectiles, we're not dealing with actual contact with the surface, the instant before contact is made. So let's see if we can find this displacement. So the how far they land from the cliff, the velocity at impact with the water. So the way that we're going to do this is we're going to treat the horizontal direction separate from the vertical direction. And I think X and Y are good labels for these two dimensions. So the horizontal dimension, X, the vertical dimension, Y. And now let's apply what we learned in kinematics with one-dimensional motion to each of these dimensions independent of one another, with one exception that we'll get to. So in the X direction, we know that we will start from rest. So we know V naught. In the X direction, V naught is 0. Excuse me. This individual is running. The initial velocity in the X direction is the 4 meters per second the individual had as they became airborne. That 4 meters per second. Now imagine this individual as they are in the air. Once they step off the cliff, they can move their little feet as fast as they want. They're not going to speed up, and they won't slow down either, because remember, there is no atmosphere in this particular class as we're learning projectiles. So with no atmospheric drag to slow them down, nothing to propel them and speed them up, their velocity will remain 4 meters per second because there will be no change in the state of motion in the X direction. And what that means is it means that this person will continue to move to the right at 4 meters per second for whatever length of time it takes to fall 8 meters. Now, we don't know X. That's what we're solving for. That's how far they are from the cliff when they land. So the time, we don't know that, how long it takes to fall, but we know how to figure that out. So now let's look at just the up and down direction and look at the same 5 variables: initial velocity, final velocity, acceleration, time, and displacement, y. We already know the displacement is 8 meters in the negative direction, but I'm going to flip that coordinate system. I'm going to say for this particular problem, and it's my coordinate system, I can do what I want, that downward is the positive y direction and upward is the negative y. And to the right is positive x, and to the left is negative x. Now, I can do this. You can do this with any problem as long as you're consistent throughout your problem and you know which direction is which. You state clearly which direction is which. I'm stating that downward is my positive direction. Now, I do this when I solve kinematics if the motion and the acceleration are both downwards. If the velocity is downwards and the acceleration is downwards, why worry about the upward direction? I simply pretend that down is positive, then I don't worry about any signs, and that seems to make it easier for me. Now, if you really want to make this a negative direction downwards, that's fine. There's nothing wrong with that. Just pay attention to your signs and be consistent. The coordinate system belongs to the individual solving the problem. So downwards is positive for me in this y dimension. So vertically what happens is the instant the individual steps off the cliff, just like the bullet that is dropped or any object that is dropped or released, you start from rest and you accelerate downwards, which I've determined to be positive direction at 9.8 meters per second squared, for a displacement of 8 meters. Now, the thing about time is that time is a scalar. So while we can separate the vectors into the horizontal x and the vertical y, the time will be the same on both sides. Because it's the scalar, direction doesn't matter for time. The motion of the projectile is the same in the x dimension as it is in the y dimension for time. So, same time. It can't possibly fly to the right for any different amount of time than it takes to fall vertically. It's one single object. So, the time is the same on both sides. So, I can get my time, I can't get it on the left side. The only equation that would work would be v is v naught plus at, but you end up with a bunch of zeros and you can't solve that. So if you look at the right side, we know y, we know v naught, we know a, and we want to know t. We could solve this quadratic. Y is v naught t plus a half at squared. We could solve this for t, and it's not even quadratic because the initial velocity is 0. So that's a 0. Y is a half at squared. If I manipulate this equation and solve for t, I think we will get t is radical 2y over a. That's 2 for a displacement of 8 in the vertical dimension, and the acceleration is 9.8. So let's see what this gets us. Somewhere around, let's call it 1.28 seconds. That's how long it takes for this individual to fall 8 meters to the water. Now, during the time that they're falling for 1.28 seconds, they continue to move to the right. So the time that I got in the y dimension also works for the x dimension. Same time, it's the scalar. It doesn't care about x and y. So for our x dimension, if there is no acceleration, look at this equation over here. That quadratic we used a minute ago, and let's write it for the horizontal here. X is v naught t plus a half at squared. If the acceleration is 0, this entire term is gone. And if v naught and v are the same, that really just means v average because there is no change. So x is vt. When the acceleration is 0, x is vt. That's like saying distance equals speed times time. So if we want x, it's 4 meters for 1.28 seconds. That's about 5.12 meters. Okay, so now we know 5.12 meters is the displacement in the x dimension. That's how far this person is from the cliff when they land in the water. Now, the velocity at impact. I want you to consider that we have two components of velocity here. At the moment of impact, that projectile is moving in sort of this direction, and it will have a y velocity component, the final y velocity, and it has an x velocity component, the final x velocity. But this hypotenuse, this velocity vector, is what we've been asked to find. Now, we already know the x component, it's 4 meters per second. It stays 4 for the duration. But the y is the final y velocity. So if v is v naught plus at, and v naught is a 0, then v is just at. 9.8 seconds of falling acceleration for 1.28 seconds. 12.54, excuse me, 12.54 meters per second. It's coming down at 12.54 meters per second. It's moving to the right at 4 meters per second. If you recall the last couple of clips, this is two velocity components, and we want this vector. So what's the resultant, or the velocity at impact with the water? Looks to me like 12.54 squared plus 4 squared is 16. This is about 13.16. Yeah, it looks good. Meters per second. So that's this hypotenuse, 13.16 meters per second. But we need the direction. Since it's not in our primary X or Y directions, we need an angle. And it's coming down. So I usually like to give the angle with respect to the horizontal. So here's the horizontal. This is the final Y velocity. Here's the final X velocity. This is the velocity vector we just solved for, the 13.16. This angle, if it's coming down, I like to say it is so many degrees below the horizontal direction. And that angle is the same as this angle, opposite interior angles. Imagine these two parallel horizontals here. So this angle, theta, is has an opposite side of 12.54 and an adjacent side of 4, and so inverse tangent of opposite 12.54 over adjacent 4 will give me an angle of that's about 72 degrees, 72.3 degrees below horizontal. So 13.16 meters per second at 72.3 degrees below horizontal. That is the velocity at impact with the water. So let's see, our displacement was 5.12 meters in the X, and our velocity at impact with the water.